from the beginning and no way from the middle, we remember our familiar parametric equation or vector equation for a circular motion, cosine t sine t, motion in a circle. Okay, what's inside the little blob here has to be interpreted as an angle. Like whatever time I plug in, even if it's a very complicated math expression, it's going to give me a single number that represents an angle because angles are what trig functions take as inputs. Okay, so if I just have t in there, what I'm really saying is whatever time it is, that's the same as what my angle, the angle to where my rider is going to be. So the angle to my rider is the exact same thing as time. And that specifies a particular motion along the circular path. But if I want my rider's motion to be different, it's like at different times, I want their angles to be not just the same as time, but other things. So let's define an a of t function that tells me my angle as a function of time. And now we can think about that separately. So let's think about these three sort of conceptually as challenges. So for this one, so for this first one, no matter what time it is, the angle is always the same. So there's actually no motion at all here. It's like I'm just at some fixed angle no matter what the time is. Here, it's like at time 0, I'm at some particular angle, but then as time increases, my angle is decreasing, which would mean I'm rotating, what's this, clockwise? Yeah, clockwise. I think it's worth thinking about slope or an approximation of slope. So let's think about units here. This is change in time. This is change in angle. So whatever the slope is here is like my angular velocity. It's telling me how fast is my angle changing per second. Neat. Okay, so for this one, it's like as time is increasing, my angle increases until it reaches some maximum, and then it decreases. So this would be a path where I'm at an angle 0 at time 0. Let's call this pi over 2 up here. So as time increases, let's call this 3 seconds and this 6 seconds. So between 0 and 3 seconds, I rotate this way. Then I stop here at 3 seconds at pi over 2, and then I go back the other way again. Okay, final question. So obviously the slope here is changing because it's not a line. But think about the slope here versus the slope here. And what question do I want to ask you? I guess I want to ask you, like, when is my angle changing faster? Is it changing faster around this time, or is it changing faster around this time? I heard it from groups close to me. So let's imagine that the change in time, the length of that base there, is always 1. So if I go over by 1 second, I guess not to scale, everybody, not to scale here. So if I go over by 1 second, here I'm going up by quite a bit because if I zoom way in there, it's approximately linear and the slope is fairly steep. If I zoom in here, if I go over by 1, my angle's decreasing, but if you sort of think about the approximate slope in that section, it's a lot shallower, which means that I'm going down, my angle is decreasing by a small amount for every second I increase. So when you're thinking about what type of curvature you want, do you want a line, do you want a curve, it's worthwhile kind of thinking about the slope in little local areas and then comparing that to your ride model and asking which of these feels more like the motion that I'm seeing in my ride. Okay, for this last part, it's something I want to show you. It may or may not be helpful for your modeling. I've said a couple of times already, to make our models physically realistic, like the way a physicist would do it, is they would set up equations about what forces are acting on your object, and then you would use calculus to derive new equations that say, okay, if we've got forces acting on your object, how does that translate into your object's motion over time? It's calculus. Differential equations. Very exciting. You can do sort of something like that without calculus, at least for the case of an object in free fall, just by thinking of the meaning of gravity and acceleration. So yeah, let's start here. So does anybody know what the acceleration due to gravity is if we're in meters per second squared? Yeah. Yeah, it is 9.8. Earlier I said 9.2 and the other teacher corrected me. So 9.8, and like meters per second squared is kind of a weird unit. Let's think about it as meters per second, which might also seem weird, but I'll tell you why in a minute. You'll notice that if you think about like simplifying this is the same thing as meters per second squared, because if I divide this fraction by another s, like now the s's are both in the denominator. Okay, so let's think about units. Here I've got what appears to be a billiard ball falling. Here's time. Here's height above the ground. Oh, nope, height above, let's call this 0 up here. Okay, so, or no, let's do this. Haha. Okay, so now it's at a height of 10 at time 0. All right, so I don't know, I'm going to do this in pencil because I want to write something here later, but let's pretend, some amount of time later, I've fallen by some amount, like, so now it's like 6. And this would be -4. Think for a minute, what is the unit for this thing? This is the change in y, but think about what would the unit for this be? So this -4 has told me I have decreased my height by 4 meters in a time duration of 1 second. So this is meters per second, otherwise known as speed. Okay, so now let's pretend that I fall even further. So let's pretend now I'm at a height of 0 after 2 seconds. So this is -6, so it looks like my speed is increasing, as it would if it was falling under gravity. So now let's see, how has my speed changed from here to here? It's like -4 to -6, that's -2. What do you think the units for this are? Meters per second. The idea is this measures my change in this number. So here, the change in meters per second, like my speed has changed by 2 meters per second, but it has done so over some duration of time. So it's meters per second. So you can think about this second order growth as acceleration. And the acceleration due to gravity is constant. So let's put all that together. Now let's erase all our numbers. I warned you that was going to happen, I think. So if we want to make this physically realistic, we know that this should be -9.8 all the time. This is going to, like, whatever we put here is going to be our initial velocity, how fast we're going to start with. And then whatever we put here is our initial height. And so then you can fill in the rest of your table here based on this constant acceleration. And then you can use your mad skills from Unit 1 or whatever to derive a quadratic equation that is actually physically realistic for that value of gravity. So I just thought that was like mildly neat. I call that 4 out of 10 neat. Oop, I should have asked you, how neat do you think that is on a scale of 1 to 10? 1? 1, 4, 6, very generous. All right. Nice. Okay.